Hello, students. We are looking at section 5.2. Um, so we're continuing from the previous section. That one was a little bit long. I think this one's going to be a little bit shorter. So just to go over the main points of this lesson, we are looking at linear relations. So as you can see, the title is Representing and Interpreting Linear Relations. So when we're talking about linear relations, we are looking at relationships that have a line of best fit that is a straight line. So that's what we mean. So if you look at the two examples here, there's a scatter plot and then there's a line of best fit that's fitted in there, and it's a straight line. Same thing here, you have a bunch of points, a scatter plot, and then a line of best fit that's also a straight line. What you can see is that these two are different. The first one, as you can see, it's, oops, let me just grab a pen. The first one is decreasing. You can see that it's going down and to the right. So that's a decreasing relationship, and this one is going up and to the right, which means it's a increasing relationship. So that's what we're going to be really focusing on. So if there is some kind of a linear relationship, we are going to use a line of best fit, like I said earlier. In the previous lesson, we did some estimating once we put a line or a curve of best fit. So if you remember what I said, when you're estimating uh, between the data, between the points that are given to you, like on this graph, here is, the first point. Actually, I'll change that. Here's the first point, here's the last one. If we're estimating between all of these data points, that's called interpolation. So there it is, interpolation, because it's inside the data set. If we are estimating outside of the data set, so here's the image here, you can see that, I don't know, I guess this is the first point, this is the last one. So outside, which is either before or after the data that's given to us, it's called extrapolation because it's external to the data that's given to us, to the points that's given to us, that are given to us. So that is general just description of estimating and their specific names, whether you're estimating inside or outside. Uh, then, let's see here. When we are analyzing these linear relationship, we already said that we're going to use a line of best fit, but we can't just draw any kind of line. There's kind of rules about it. So when you're drawing a line of best fit, you should definitely use a ruler. It should be straight. It shouldn't be a freehand line of best fit. And you should try to go through as many points as possible if that's kind of doable. But it should also be balanced. You should have some points, where is it? You should have some points above, you should have some points below the line so that it is balanced. You shouldn't have too many below and not a, not a lot, not enough above, that sort of stuff. And you shouldn't just do a line of best fit that just connects first and last points. That makes no sense. One last thing that's not written here is that line of best fit doesn't have to go through 0, 0. So a lot of times I see students that, let's say we go to this graph over here. I see students that they force a line of best fit. They take a ruler and they start here and they say, oh look, it's a line of best fit because I have some points above, some below. That's balanced. No, that's not the case with the line of best fit here. It has to follow the trend that the points are representing. All right, and then there's a little bit of interpolation is inside estimating, extrapolation is external estimating, that sort of stuff. But I already mentioned that. So let's look at the example that they have. They have an example of the operator of an ice cream truck keeps track of how much ice cream is sold on days with different temperatures. She records the sales for the past 10 days. So here we have two variables. We're comparing two different things. We have temperature, which is in degrees Celsius, and sales. So first thing we should ask ourselves, which one of these depends on the other? So if I'm selling ice cream, am I going to sell more ice cream on cold days or warm days? So, or is the temperature going to depend on the number of ice creams I sell? So hopefully you realize that the sales, the number of ice creams, will depend on the temperature, and hopefully you can kind of predict and say that on hotter days, there's going to be more ice cream sold, because not a lot of people are eating ice cream on cold days. So this is our table of values. It's a horizontal table of values. And like I said in the last lesson, if you want to rearrange this, you can create the vertical one. So in this case, we would have temperature. I'm just going to put T for temperature, and sales, I'll put S. And then you can rewrite it. So temperature of 14.4, 215 ice creams sold, and 16.2, 325, so on and so on. So, if I'm graphing this, I know the temperature is my independent variable because the sales depend on the temperature. So this is my independent variable, which means that this is going to be on the x-axis, and sales is dependent, so this is going to be on the y-axis. So I would create a scatter plot, which they already did here in the solution, so it looks something like that. They created a scale, as you can see, for both temperature and ice cream sales. And then they put a line of best fit. So we have a line of best fit, and we can look at some trends. And hopefully you can see right away from the shape of this graph, you can see that it's kind of pointing up to the right, which means that there's an increasing relationship. So we can say right away, okay, the hotter it gets, so you can see as the temperature increases, the more ice cream is sold. So that's the kind of relationship that we have, and we can answer, I think it's in B, it says what kind of trend is happening. So we can see that the trend is that the graph is going up and to the right, and there's an increase in sales as the temperature increases. So that's what we're talking about. The weather, the next one, it says C. The weather forecast says the temperature will be 35 degrees Celsius today. Estimate what sales the operator will have today. So this is the estimating part. So if I know that it's going to be 35, let's say 35 is here, I'm going to be estimating, you know, for this temperature. This temperature is after my data set. So when I'm doing my line of best fit, I do want to extend it for that estimating. So it should be something like this. I know that they have a solution on the next page, but I'm going to show you just, how we can do it from scratch. There we go. This looks better. So that's kind of my extended line of best. Oops, that's not what I wanted. It's my extended line of best fit. There we go. So if I am estimating for 35 degrees, I'm going to take a dotted line. So I'm taking my ruler, I'm going vertically 35 degrees, and then I'm going horizontally over. And this is going to be my estimate on how much ice cream. So it looks like it's 900 and I don't know, 70, 80, let's say estimate. I think they estimated 980. There we go. So they estimated around 980 right here for 35 degrees. And they just did it like that. They went up and over, and they got 980. For the next part of the question, it said it's kind of in reverse. If they want to achieve $500 in sales, so we're going to start on the opposite. We're going to start on the y-axis. So you start here, you draw your little horizontal. I'm just going to improvise it here. And then you draw it down. And then you can estimate what the temperature is here. And they said it's around 22 degrees Celsius. So you can go starting from x to y or starting from y going to x. And that's pretty much how we analyze these linear relations. A lot of these questions are going to be the same. The process is the same. So as you get to do more of them, you'll be more comfortable. All right, so here's our practice question. So it says the first 5 positions in a pattern are shown. So what that means is we have 5 positions. There we go. 1, 2, 3, 4, 5, which in the table it kind of translates like this. Um, because we're looking at position number, that is going to be our x-axis. That's going to determine what kind of number of these cubes or squares we have. Number of squares, yeah. So now we're going to fill in the table. So we're going to go and count the number of squares for the first one. So we have 1, 2, 3, 4. I didn't press them. There we go, 4. So there's 4 here. There we go. That's going to look better. There's 4. On the next one, there's 1, 2, 3, 4, 5, 6, 7. There's 7. There we go. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hmm. 1, 2, 3, 4, 5, 6, 7, 8, 9. 10, 11, 12, 13. So I would ask you to kind of pause the video here and without counting, maybe predict what the fifth position is going to have. How many squares is it going to have? You might see some kind of a pattern happening here. If you look at the first one, it's 4, next one, 7, 10, 13. Hopefully, pause the video, and I'm just going to continue talking. You can unpause me. Um, it looks like it's increasing by 3 squares for every position. So that means the next one should be 16. So if we count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There we go. So because this is a linear pattern, it means that we're going to have a straight line. We should see the same number increase for every position or decrease depending on what kind of question we have. In this case, it's increased by 3 every time. So it says, for B, it says draw a scatter plot and draw the line best fit. So like I said, position number is X, number of squares is Y. So there is let me write it here, position number, and this is number of squares. There we go. We need to make a scale. Position number, super easy, but okay, well, not so easy. Um, Here it says extrapolate to determine how many squares position 7 will have. So that's a later question, but what I was going to do, I was going to say, okay, well, this is going to be 1, 2, 3, 4, 5. That's great for me graphing all this data in the table, but I'm going to have to estimate, and I'm not going to have enough information here. So what I'm going to do is I'm going to have to adjust it and make the scale a little, it's going to look bad because I'm going to make the graph shorter, but I will be able to estimate later on. So what I mean by that is, let me just adjust. 1 square is going to be 1 position. So 1, 2, 3, 4, 5, 6, 7, 8. So you can see the graph is going to stop here, which is going to be really short, but for the purpose of this lesson, I will draw it like that so that we can estimate further information. All right. Number of squares goes from 4 to 16, but because I'll be estimating as well, I will kind of adjust that on the y-axis as well. So let's see how many we have here. 2, 4, 6, 8, 10, 12, 14. So that's no good. So maybe we'll go by 2. So maybe this is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, and 28. There we go. And now we're going to graph. So for the first position, it was 4. Second position, it was 7. So in here, third was 10. Fourth was 13. Fifth was 16. There we go. And it does say line of best fit. Now you can see because this is a perfect linear relationship, all the points are actually lined up perfectly. So my line of best fit, when I do it, it should go perfectly through all of them. There we go, something like that. And I'm going to extend it all the way up. There we go. So that is my scatter plot with the line of best fit. So that checks off B. There we go. B is done. Check. C, determine if there is a trend in data, and if so, what kind of trend. So as the position number, well, as the position number increases, what's happening with the number of squares? You can see that our graph is going kind of in this direction. So graph is going up and to the right. There we go. And our relationship is as the position number increases, number increases, the number of squares increases as well. I'll put number of squares. As well. And you can actually be specific and say that for every position number increases by 3 squares, but for now it's all right. Then the part D says extrapolate to determine how many squares are position 7. So that's kind of what we were preparing for in terms of our graph. So you take your ruler. I'm going to use a dotted line. Start at 7. Going to go up vertically here and over. There we go. It looks like 22. So how many squares? There will be 22 squares. Let me just put this. 22 squares. Now, is there another way I could have done this? Yes. I could have just kept going with my table of values here and had, 6 and 7. So 16 plus 3 is 19. 19 plus 3 is 22. So that would have been another way. But we're extrapolating by using graph. So the next one says extrapolate to determine which position has 28 squares. Okay, so this is a kind of a reverse thing. We're looking at squares, which is, let me just get my graph, my line here. There we go. So starting at 28, so I'm going to go to my line of best fit, a horizontal line, and then down. There we go. So that's how many there will be. That would be 9. So what position? Position 9. Could I estimate it another way? Yes, I could keep going on my table of values here and just kind of keep adding. So 22 plus 3 is 25. 25 plus 3 is 28. And just keep adding on. So you can get, the whole table of values forever and ever. Just keep adding 3. But the problem is going to happen at one point where it says, well, what about 100th position? And you're not going to want to, draw not draw. You might not want to write the table with 100 positions. You might take up take up a whole page or two. So what we're going to do is we're going to use equations. Anyways, we're going to get to that eventually. So I think that's it. So try out the EQR preparation questions. Some practice here. They're pretty basic, and I will see you in 5.3.